solutions. And first off, solutions is really what we use for that sort of aqueous symbol. The exam is going to be after spring break. Yeah. So as I said earlier, it's not going to be next week, but next Wednesday we are going to have a quiz on nomenclature just to make sure, you know, everybody's on the same page. We will have a quiz on Wednesday on that nomenclature part. So just the naming, every naming that we talked about, you know, is possible. So aqueous solutions are basically what solutions are. They are the ones that get that AQ symbol. And that AQ symbol means aqueous. And there is a difference between aqueous and somebody that gets the L symbol. Somebody with the L symbol is a pure liquid. So for example, if you had just water by itself, that would get the L designation. If you actually take something like water and you add something like, say, solid sodium chloride to it, the salt will dissolve in the water, and that will make a sodium chloride solution that will get the aqueous symbol next to it. So aqueous usually means that we made a solution, and usually a solution is made by dissolving like a solid in like water or something of that nature. Now, a solution is a homogeneous mixture, which means when we mix it, it all mixes together. There's actually two parts to a solution. The smaller part is known as the solvent. I'm sorry, I already sneezed, excuse me. The smaller part is known as the solute, while the larger part of the solution is known as the solvent. And in the example here of the sodium chloride solution, water would be the solvent. And water is a very common solvent for a lot of reasons. And the sodium chloride would be the solute in that case. The easy way to figure out which one's the solute is it's always the name of the solution. So if you had a sodium chloride solution, the solute would be sodium chloride. If you had a potassium chloride solution, it would be potassium chloride as the solute. Water is oftentimes used as the solvent, but water doesn't always has to be the solvent. But in a lot of cases it is. So sometimes people think water always has to be sort of the solvent. Doesn't, but it is used a lot, and it's used a lot with things that are ionic because it works really well for those guys. Here's an example. If we take some water, which in this case would be the solvent, this would be our copper 2 sulfate. This is sort of like the solid or the blue guys that are there on the bottom, and that would be our solute. When we mix them together, basically all the solid dissolves and we get this nice kind of blue solution, which is aqueous at that point. Water is a really effective solvent, and because we switch books there, we haven't talked about this yet, but I actually have talked about it. We did bonding. So water is polar, and if you remember, water, which is polar, basically means that water has a side that's more negative and a side that's more positive because of that unequal sharing of electrons. And it's the hydrogen side that's more positive, oxygen side more negative. And when you take something that's ionic, like sodium chloride, and you dissolve it, basically it breaks apart into its ions. And what ends up happening is like the positive ion gets surrounded by the negative side of water. And the negative ion, like the chloride ion, gets surrounded by water, but it gets surrounded by the hydrogen part of water. And water does two things. That is actually what's happening when we dissolve something. That's why it looks like it all disappears, but it really doesn't disappear. It just gets mixed up with all those waters that basically surround it. It also prevents the positive ion and the negative ion from coming back together, because if the waters weren't there, they would definitely want to come back together and they would make a solid at that point. And again, that is why it kind of looks like the solid. When you take a salt or something, it disappears, but it's actually still there. Also why when you take something like salt water and you heat it up, when you heat it up, you're essentially removing all these waters, right? You're evaporating them off. And when you do that, the only two things that are left at that point is the positive ion and the negative ion. and there's no waters in the way to stop them from coming back together. And because basically you got rid of all these guys, you know, it's like free season. They could definitely come back. And that's why if you've ever evaporated off salt water, you will end up getting the solid back, because all the water just evaporated off. They're no longer going to be separated from each other, and that solid comes back. And that's why when we talk about dissolving something, it's actually a physical change and not a chemical change because of that, because it's still there. We could get it back, obviously, by evaporating off the water. Any questions in that? Here's sort of an example of that. You know, water basically comes in and just starts plucking off some ions, basically, and they surround each of those ions, preventing those two ions from coming back together. We help this along, right? Because when we go to dissolve something, we start stirring it. When we start stirring it, it throws a bunch of waters all over the place, also provides a lot of energy, and it allows this basically solid guy to come apart a lot quicker, right? And that's why when we kind of stir something like a spoon or something like that, the salt and stuff can dissolve a lot quicker than if you just kind of tossed it in there and waited for sort of it to naturally do that. It takes a much longer time. Again, by kind of mixing it and stirring it, you're adding more water all over the solid, going to allow this interaction to occur a lot quicker. Here's another picture in case you didn't like the first one. Here's a third picture in case you didn't like the first two. I understand sometimes we want more pictures. And this is basically the same idea here. Something like that. I don't know if you get all that to dissolve in there, but you know, you would definitely get at least some of it to basically dissolve. But the idea is, as it's dissolving, it's basically the solid going into the water kind of three-dimensional structure of water. And that's really why when we look at it, we sometimes perceive it as it just disappeared. It was gone. It must have chemically reacted because it's just gone. I don't see the solid anymore. But again, it's really still there. We just can't really see it at that point because there's a ton of waters basically surrounding each of the ions. And basically to us visually, we can't actually see that. And again, that's why it's more of a physical change than obviously a chemical change. So let's talk about solubility of things in water. Solubility means if something is soluble, it means it will mix really well. If a solid is soluble in water, it will dissolve. If a solid's insoluble in water, it will not dissolve. If two liquids are soluble in each other, that is what is sometimes referred to as being miscible. And if two liquids are soluble in each other, it will look just like one liquid. If two liquids are insoluble in each other, they're sometimes referred to as being immiscible. And if you have two liquids you put together and they don't mix, you'll see layers basically start to occur because they really don't mix with one another. Ionic substances, things that are ionic, are always soluble in water. Things that are non-ionic are also soluble in water, things like sugar and ethanol. So even though sugar and ethanol are not ionic compounds, they are still very soluble in water. And the real reason for why they are soluble in water is if we draw the structure of something like ethanol, for example, it will look something like this. And pretty much, if you remember from bonding, all the carbons and hydrogens on this side, these guys are pretty much nonpolar. So that's all nonpolar part. But what ethanol has that makes it very soluble in water is the fact that it has that OH group. So at the very end there, it's got this OH group. And this OH group is a polar group, like we talked about with bonding. So this is polar, which means when a water molecule comes by, that also is positive on the hydrogen, negative on the oxygen. This guy is negative on the oxygen, positive on the hydrogen. They are able to come together and do what is known as hydrogen bonding with each other, which is a type of interaction that occurs, and that makes it very soluble in water. So even though it's got this like nonpolar part, because it's got this little part there that looks, and if you even look at it, it looks just like the bond you see in water. It's the same OH bond that you see in water. And they're able to interact with each other because it contains that particular bond. That type of bonding is what's known as hydrogen bonding, and it makes it very, very soluble. Sugar as well has a ton of OH groups all over it. So everywhere there's an OH groups, it makes it really, really soluble with each other. And here's that process of dissolving. This is methanol. Again, methanol here has a carbon and hydrogen, but it has that OH group, and this oxygen is more negative, hydrogen is more positive, and that's going to give it that opposite attraction there. That's going to allow it to interact. It could also interact with another water here, and that's going to increase the solubility of something like methanol in water. Here's that ethanol that we basically just drew. But what about oil and water? Well, if we take oil and water, though, they really don't mix. And why does oil and water really not mix? It is because oil and water, or oil actually, oil itself is really nothing more than a super long continuous chain of carbons attached to carbons, and attached to those carbons are hydrogens. I won't draw them all, but these are all hydrogens all the way across, up and down and across. And again, that carbon hydrogen bond is nonpolar, which means this molecule is nonpolar, which means essentially it has no charge. It's kind of neutral. So when water comes by, it's looking to do like a positive negative attraction, and it's got like no way to do that. It has no way to interact with each other because there's really no positive side to oil, there's no negative side to oil. It's really sort of neutral in that sense. And that's why what we see, if you ever see oil in water, oil tends to kind of float to the surface because they have no way to interact with each other in a long period of time. And it brings up the idea when we talk about solubility of what is known as like dissolves like. And what that means is things that have similar types of interactions with each other, or that can interact with each other very similarly, they're going to be very soluble in one another. They will mix. Like we saw with the methanol and the water, it had that OH group on the ethanol. And that was the part that was able to interact really well with a very similar type of group of water and made it very soluble. Here, when we look at something like oil, it's got none of those groups. It's got no way to interact with it, and it will not interact really well. So what does that really mean? Well, there are things that are what are referred to as being polar. So if you have something that you know is a polar thing, and you mix it with something that is polar, it is going to be soluble in each other. If you have something that's ionic and you mix it with something that's polar, it is also going to be soluble in each other. And this is like in bonding when we talked about molecular polarity, if the molecule is polar or nonpolar. If you have something that is nonpolar, it will actually interact with something else that is nonpolar as well, and they will mix as well. So these three sort of interactions will result in something that will be soluble in each other and will mix. You only run into trouble when you try to cross over. Like things become insoluble when you take something that is polar and try to mix it with something that is nonpolar. Like what we have on this example here, oil being nonpolar, water being polar. These two guys do not mix because of that. So you oftentimes hear in terms of solubility that term like dissolves like, and that's basically what it means. It basically means that, you know, if you could find a couple of things that have a very good way to interact with each other, similar ways to interact with each other, then they will mix. And if you have two things that really are sort of opposites of each other in terms of their ability to interact, they're not going to be able to interact with one another very well. Any questions on that?
Okay. Could you give examples of like the polar mixed with polar, ionic mixed with polar, and then nonpolar mixed with nonpolar?
Yeah, so for example, say polar and polar would be kind of what we were just talking about. So like methanol, that or ethanol, that little picture where that guy had the OH group and water. Those would be two polar guys. Ionic and polar would be something like sodium chloride and water. And nonpolar, you know, would be something like, say, oil if you want, and something like hexane, for example. Hexane is also just like 6 carbons and hydrogens. You can even see it kind of even looks like each other. And those guys would be soluble in each other because they're both basically nonpolar. And they are able to use what is known as dispersion forces. And we'll talk about that in a later chapter. But they're able to use a similar type of interaction with each other. And this is hexane oil. Again, it's a really long guy like that. Those two guys would be soluble in each other because, again, they kind of look like each other if you want to think about that, or they have very similar parts to each other. And so those would be some examples. Obviously, things that are insoluble would be like what we have on the bottom here, oil and water. You know, they don't mix because one is polar, one is non-polar. Other questions?
Thank you.
You're welcome. Other questions on that? Okay. Now, this is a picture up on top of sugar. And again, sugar, although it's a long thing of carbons and hydrogens, the one thing that makes it really soluble in water is if you look all around here, it's pretty much littered everywhere with all these OH groups. And everywhere there's that OH group, it basically has this bond. And everywhere that OH group is found, that means when a water comes by, again, when we look at it, it's able to interact with each other because this is negative and that's positive on water. That's positive, that's negative. And you got this kind of opposites attract between the oxygen and sugar and the H in water. So everywhere I circled, pretty much water molecules can interact. And that's what makes it really soluble because all over pretty much it has a way to interact with it. Even though it's a relatively large molecule, it's able to do that. Here's a much prettier picture of oil than what I drew on the previous slide, but the typical thing that you see here is just all carbons and hydrogen bonds and carbons and carbon bonds, and those are all non-polar bonds. So remember, when we talked about non-polar, that means equal sharing of electrons as a whole over the entire molecule, and that basically gives oil, you know, a non-polar, neutral, no charge happening. And all interactions that occur basically between, you know, one type of molecule and another when they come together, all interactions are essentially based off of a very simple concept, and it's that opposites attract concept. You know, just like we see here, there's a negative side here attracted to a positive side here. And all interactions when molecules get together basically occur that way. Even oddly, non-polar guys are able to do that for a very short period of time. And again, we'll talk about that in a later chapter. But as odd as it sounds, even though they're kind of neutral, they're able to very temporarily get into a positive negative situation. And that's also why if you've ever done, like, say, oil and vinegar salad dressing or something like that, and you mix it, it does mix for a bit, right? But if you put the salad dressing out, everybody sort of separates out to their different layers. And that's because over a long period of time, the oil and the vinegar, which is polar, doesn't have a way to interact with each other like for a very long period of time. They could do a very short period of time, and that's why you get a little bit of mixing that occurs. But eventually, if you leave it alone, it will sort of separate out. And that's because, again, and again, we'll talk about it in a later chapter, they don't have a really long range way of keeping that interaction together. And it's because really the oil lacks the sort of positive negative side that occurs. And that's what we typically end up seeing with oil and water. We get the oil on top. The water part is typically on the bottom. Usually when we get that sort of combination, non-polar ends up on top, polar part ends up on the bottom there. So when we talk about solubility, as I mentioned earlier, there's a couple of terminologies that we use. And again, if something is soluble in something else, or mixes in something else, that is said to be soluble. We usually use soluble a lot of times when we talk about a solid dissolving in a liquid. We sometimes use the word miscible when we're talking about, again, two liquids together that mix. If something really doesn't dissolve in another or mix in another, is said to be insoluble. And that's like our oil and water example. There's usually a limit to the solubility of a substance. So, you know, if you take sugar packets and you keep dumping it into the bottom of a glass of water and a whole thing of sugar, and you just keep dumping it in, dumping it in, dumping it in, at some point there is a limit to how much solid you could get to dissolve in a liquid at a given temperature. And that's what's sometimes referred to as sort of the solubility point there, the saturation point. There's a point where, you know, you're not going to get anything else to basically dissolve. Gases are always soluble in each other, but that's because they're constantly flying around. So as the gases are flying around, they're just by that process constantly mixing with each other, which means that they are constantly soluble in each other. And that's just the presence of the gases as they're flying around, basically mixing with one another. But how do we know if we kind of put two things together, will we get a solid or not a solid? It was sort of a question I think earlier today in lecture. And we can use something that's known as solubility rules. This is not necessarily from your book. You have a similar table, I think, in your book, but they're all sort of the same. There are certain things that are always soluble. So things from group 1 of the periodic table, things that have ammonia in it, things that have nitrate in it, there's absolutely no exceptions for any of those guys, which means if you see a chemical formula that contains any of those things, it will be soluble. And how we represent that in a chemical formula is with the aqueous symbol. Chlorides, bromides, and iodides are also soluble in everything, but there are 3 exceptions, which means if we ended up with chloride that had silver in it, it would not be soluble, but would be insoluble. And how we represent insoluble is with a solid symbol next to the formula. Now, there are sulfates are typically soluble, but there are some exceptions: calcium, strontium, barium, and lead. And then there are some things that are typically insoluble, which means these guys typically make solids. These guys up here typically make aqueous, unless they are one of these exceptions. Things in group 1 are ammonium, are the exceptions, which is the same as what we have on top. And things in group 1 are strontium or barium are typically exceptions to it. So how do we use this? Well, if we look at one of those type of reactions, and it typically will be one of those precipitation reactions, for example. And if we take something like silver nitrate and I react it with sodium chloride, by the way, from our conversation earlier, you should recognize this as a double displacement reaction, positive, negative, going to give us silver chloride plus some sodium nitrate as the 2 ions basically swap partners. So how do I know, you know, what each of these guys are going to be? Well, I could look at what is there and compare it to the solubility table to help me decide. So when we look at the first one there, we have silver and we have nitrate. And you may not be able to find both of them on the chart, but you should at least be able to find one. And the one that I can find is nitrate. And when I look at nitrates, there's a very bad circle there. When I look at nitrates, I see that it is soluble in everything. There are no exceptions over here, which means I know this guy is going to be aqueous or a solution when I begin. Question on how I got that there. I then could look at the next one, which is sodium chloride, and I could look at sodium, and I see sodium as group 1, which means it's going to be soluble, and there are no exceptions, which means as soon as I see sodium in the formula, I know that guy is going to be aqueous. I look at silver, and I might not be able to find it on the left-hand side, but I can find chloride on the left-hand side. Chlorides are soluble, but there are some exceptions, and silver happens to be one of the exceptions. That means that normally chloride would be soluble, but because silver is an exception, that means chloride would actually end up being insoluble. And that is actually the solid that would be formed here. And when I come over here, I see sodium like we talked about before, soluble, no exceptions, going to be aqueous. So sort of an earlier question was, how do we know, what everybody's going to be? That's sort of how we know. We could use these solubility rules to determine what is going to be a solid and what's going to be aqueous in this case. Any questions on that? Let me give you one here to look at and see how you do. Let's do that. And let's do this. And let us do this. And let us do this. So use the table there and determine which ones are soluble and which ones are insoluble. And I'll do the balancing thing here. There you go. So take a minute there and see what you come up with. Aqueous and soluble. When I look at potassium iodide, I see potassium here, which is group 1, soluble, no exceptions, will be aqueous. Again, I may not be able to find lead on the left-hand side, but I can find iodide, which is right here. Iodide is soluble, but there are 3 exceptions. And actually, lead is one of those exceptions. And because it's an exception, iodides are normally soluble, but the exception makes it the opposite, and it will actually be a solid in this case. It'll be a yellow solid in this case. When we look over here, potassium is as far as we need to go. No exceptions, going to be soluble. Any questions on how to use a solubility table? It would obviously be provided for you if you needed to use it. Any questions on that?
Excuse me, Professor.
Yeah.
The lead in with the nitrate, how come that one is not a solid?
It's not solid because it contains nitrate, and nitrate is 100% soluble. There's absolutely no exceptions, which means when you come across any of these guys here, pretty much as soon as you see any of those guys in the formula, you don't even have to think about it. It's going to always be this, because there's no exceptions. They're always going to be soluble because of that. So that's why the lead with the nitrate's good, because nitrate's soluble. But when the lead hooks up with the iodine on the other side, it becomes something that is insoluble, unless it's yellow type solid that actually forms.
Okay, thank you.
You're welcome. Other questions on that? Okay. Then let us continue on here with solutions.
Professor, I have a question.
Yeah.
Down where it says, down where it says like carbonates and phosphates and hydroxides, it says insoluble group 1A.
Yeah. So what this means, if that's what you're asking, is anybody that has carbonate, phosphates, or hydroxides in it are typically going to be insoluble, which makes a solid.
Okay.
The exception would be if you have, say, sodium carbonate, because it contains sodium from group 1, it would go from being insoluble to something that would become soluble. And that rule agrees with this rule here, that everything in group 1 is soluble. So on the bottom 3, these are guys that normally are going to become solids. They will not become solids if they have anybody from over here in the formula. And that's why, for example, I don't think we have any of those here, but that's why, for example, if we had something like sodium hydroxide, sodium hydroxide is a base and it is soluble. Hydroxides are normally insoluble, but because in this particular case, it's hooked up with sodium, sodium is part of group 1.
It would make it soluble.
It's soluble. It's basically the opposite. So if you want to think about these 2 columns, this is typically what it normally is, this column. So if it's soluble, it's normally going to be aqueous, all these guys. If you happen to have somebody in this column, it becomes the opposite of what it is in the first one. So if it's normally aqueous, but somebody on the right-hand side is in there, it then becomes solid. And if it's normally solid and you have somebody on the right-hand side, it becomes aqueous on the other side.
Great. Thank you.
You're welcome. Other questions on that? Okay. Then let us continue. So as we talked about solutions and solubility, you know, when we talk about solubility, it is that like dissolves like that we hear a lot all the time when we talk about solubility. And again, the way to remember sort of what that means is when you look at something, you know, if they really do sort of look kind of similar or have similar types of bonds, they're going to be able to interact well with each other. The solubility of a solute depends on the temperature. Typically, if we have a higher temperature, we get a larger solubility of a solid in a liquid. And what that means is, you know, if something's not dissolving, sometimes people say, just kind of warm it up a little bit. And when you're warming it up or increasing the temperature, what you're doing is you're increasing the energy, which means everybody's moving around faster, and that's going to allow really things to dissolve a lot more. When we have a lower temperature, we have a larger solubility of gases and liquids, and that's because gases are normally flying around, right? So if we lower the temperature, the gas molecule is going to move a lot slower because it has less energy. And it's going to be in the water part or liquid part a lot longer than it would if it was higher temperature and it just kind of flew right out. And that's why at lower temperatures, we see gases dissolved a lot more in the liquid. Also, pressures with that, when we have very high pressures, you have a lot more of gas molecules dissolved in the liquid part. Common example of that is your soda, right? Before you pop the top on your soda, you have a lot of CO2 dissolved in the liquid. Once you pop the top, you release the pressure. Also, that's all the fizzing you see. It's all that CO2 coming out basically from the top when you pop the lid there, or not the lid, I guess the flip cap part of it, and for that particular reason. When we talk about solutions, we also sometimes will describe solutions a couple of different ways. And one way is what's referred to as a saturated solution. And in a saturated solution, what we end up with is a solution that has the maximum amount of solute or solid, basically, that will dissolve at a given temperature. So solubility is based on temperature. And if we have hit what is sometimes referred to as the saturation point, that means right at that point, we have pretty much hit the part where if I add more solid to it, it will not dissolve anymore. It will start piling up on the bottom. So before we get to that point, we have a situation which is known as an unsaturated solution. And an unsaturated solution means you haven't really hit that point yet of it stopping to dissolve. So it will continue to dissolve if you put more solid in it. So you can kind of think of it like this, you know, this is a saturated solution. Everything's dissolved, but we pretty much have maxed out in terms of how much we could dissolve. Before we get there, we have an unsaturated solution where we could still add. We haven't really maxed it out yet. And you can continue to add solid to it, and it will continue to dissolve until it hits a saturated solution. And it's at that point, nothing else is going to dissolve. It's going to basically start piling up at that point. So saturated, nothing more will dissolve. Unsaturated, we have definitely hit the point of, I'm sorry, make sure I said that right. Saturated is the point where nothing more will dissolve. Unsaturated, we haven't hit that point yet, and it will continue to dissolve until we hit that saturation point. In your book as well, there's actually, you know, there's values for these things in terms of solubility of things. They'll sometimes say, hey, this substance has a solubility of, you know, 125 grams per milliliter at, you know, whatever, 25 degrees Celsius, milliliters of, say, water, right? And what that means is, you know, if you wanted to say dissolve 400 grams of this substance and, you know, 20 milliliters of water, could you do it? You know, and you could use this as like a conversion factor to figure it out. We know that if I have 100 grams of the substance, if I wanted to dissolve 400 grams of my made up substance, and I know that my substance, I could dissolve 125 grams of it in a milliliter of water, and I just made that up, so we'll see what we come up with. That means that I would technically need 3.2 milliliters of water to get that to dissolve. And the question asked, could you dissolve that in 20 milliliters of water? And the answer would be yes, I could, right? I would have no problem doing that, right, in that particular case. Now, if I change that and I wanted to do 4,000 grams of my substance in that same 20 milliliters of water, could I get it to dissolve? We could do the same calculation if I had 4,000 grams of my made up thing, and using that as a conversion factor, sort of the solubility of it. What this would tell me is if I took 4,000 grams of it and divided by 125, I would need 32 milliliters of water. And in that particular question, the answer would be no, it would not basically dissolve. Right around, you know, at 20 milliliters of water, it would definitely would not dissolve in that particular case. Question on that? Yeah, it's just made up. Yeah, I just made up. Actually, I made up both of these numbers. Yeah. So I just randomly made it up. There's an actual table that has real numbers and real values, but you could actually do a calculation to figure that out. I made up all these numbers. It's probably not in that table for sure. Maybe it is. I don't know. Maybe there is something like that. But you can actually find sort of values, if you will, for solubility, and it will, you know, you could kind of do a calculation and figure out, you know, do you have enough? Could you dissolve that much? How much would dissolve, for example? You know, you could do the opposite thing. Like if you had, say, 20 milliliters of water and you want to know how much maximum could you dissolve in that, basically you could use the same sort of calculation. You could start with the 20 milliliters of water and use our little conversion that, again, I made up, which is a milliliter of water is 125 grams of this made up substance. And basically what that would tell you is if you had 20 milliliters of water, you can maximally dissolve in there about 2,500 grams of this made up substance. And at that point, up to about 2,500 grams at 25 degrees Celsius in my made up example here, all of that 2,500 grams should dissolve. If you decide to go to 2,502 grams, you'll get 2,500 grams to dissolve, but 2 grams of it will not dissolve in that 20 milliliters of water. So again, you could kind of use values, you know, that you could be given to you in a problem and do some calculations. And they're really just conversion sort of calculations to figure out, you know, how much you could dissolve and what some things actual solubility are. Question on that there. Okay. Now, there are a couple other common ways we describe solutions is concentrated or dilute. When we talk about a concentrated solution, that is something that has a lot of solute dissolved in a very small amount of solvent. So there's a lot of solute dissolved in that. It's very concentrated. And that's how a lot of chemicals come. They're naturally come as concentrated solutions. And then we sort of do the second thing to them. We take them and we dilute them. And when we do a dilution, basically the only thing we obviously will do is add more solvent in a dilution. And what that ends up doing is it makes a smaller amount of solute in that solvent. And basically the concentration goes down. It's sort of just like when you buy like a drink, you know, with some ice in it, and then you decide to go to a class and you leave that drink in your car. When you come back, all the ice has melted at that point, right? Because it's a hot day. All the water from the ice as it melts will then dilute your soda down. And, you know, you take a drink, you're thirsty. You go, how bad could it be? And then maybe you regret it afterwards, right? But you try it at least, right? And it doesn't obviously taste as good as it did probably straight from the fountain with, you know, not so much melted ice in that particular case. So that's sort of an idea there between concentrated and dilution. That's right. So yeah, so you add some water there to your Kool-Aid. Yeah. All right. Any questions on that? And electrolytes are really substances that when they go into water, will break apart into ions. And there's a few different types of electrolytes. There are ones that are referred to as a strong electrolyte. And a strong electrolyte is something that when it goes for a swim, basically in water, it 100% breaks apart into ions. So something like a sodium chloride solution, not a solid, but an aqueous solution of sodium chloride. When it's actually in the solution, it's actually not this at all. It actually will 100% break apart into sodium ions that are surrounded by water and chloride ions, which are surrounded by water. So 100% of what you have in a strong electrolyte solution of sodium chloride is those ions floating around. You have absolutely zero of these guys floating around in an actual solution of sodium chloride. And that's, again, once it's been dissolved, that's essentially what you got going on there. Hydrochloric acid, which is a strong acid, this is hydrochloric acid. When it's in solution, it also 100% breaks apart into the ions, and 100% of what you would have in that solution are these ions. Why is that important? Well, the other part of the definition of an electrolyte is when it breaks apart into ions, it is those ions that help conduct electricity. Basically, the presence of those ions floating around kind of completes the circuit, if you will, and electricity is sort of made there. And what that means is, and I won't draw it because I learned over the years not to draw a very bad looking light bulb. But if you had a light bulb, for example, I'll just make it a circle. This light bulb would then go off very brightly. So if you stuck like an electrodes, this light bulb hooked up to some electrodes that would go into a solution that is a strong electrolyte, this light bulb would go off very brightly. So it would be very, very bright. And that's because that solution has a lot of ions that are floating around, and those ions help conduct electricity. And again, you, in terms of a light bulb sort of example, which I think is what they do in the lab, you will see it shine very brightly. So if you're kind of doing a lab part or something like that, or looking at that sort of experiment, and you see the light bulb is very, very bright, you will have a strong electrolyte, which means when you write the formula, a couple of things will look like. It will have a one-way arrow, and it will have all the ions on the right-hand side, and this guy will be together on the left-hand side, and that will be your strong electrolyte. There's also what are referred to as weak electrolytes. Weak electrolytes break apart a little in water. It will produce a few ions. So an example of that would be something like hydrofluoric acid. Hydrofluoric acid is actually a weak acid, and when it breaks apart into H plus and F minus. The difference here is a couple of things. You only produce a few of these ions are produced. What you mainly have in this solution is like this guy. This is pretty much mainly what's floating around that solution. So unlike up here where you have a lot of chlorides and sodium ions pretty much floating around, if you were to kind of redraw this guy over here, and again, my wonderful drawing of a light bulb, also known as a circle with the word light bulb written inside. And you got some electrodes coming down in that solution. What you would mainly have in this solution is a lot of HFs floating around. But occasionally you'll have a couple of, maybe some fluorides floating around, some H pluses floating around, but nowhere near as many ions as you would have floating around, say, in this solution. You have a lot of those ions floating around. So what does that mean is it's still able to produce a few of these ions floating around in the solution. So because it's still able to produce a few of those ions, it's still able to conduct electricity, but it's going to give you more of a dim light bulb when the light bulb goes off. So it's going to be very, very dim when you look at it. It will still go off, but it will be nowhere near as bright as in a strong electrolyte. And that's just because of the fact that in a strong electrolyte, 100% of it, it's all pretty much going this way, and you have 100% ions in there. In this one here with the weak electrolyte, it is actually what is referred to as a reversible reaction. And that is why when you look at the arrows, which is a big hint here as to it is a weak electrolyte, the arrows are actually arrows heading in both directions. And that is different than a strong electrolyte where the arrows are heading in only one direction. So that's a very key way that you can identify something as a weak electrolyte. If you see these arrows, it implies a reversible reaction. And what that means is in this reaction, things will go in the forward direction, which is going from reactants to products. But at some point, those products will come back together and head in what is referred to as the reverse direction and actually remake the reactants from where it came from. It's like a back and forth type situation that's occurring. And that's why we see two arrows. And those two arrows are only for weak electrolytes. So if you see a reaction in the lab manual and you see those two arrows, you don't even need to think about it. It's going to be a weak electrolyte. Again, it will still break apart into ions. But what you mainly have is that whole thing kind of still staying together. And that's different than in a strong electrolyte where 100% of it breaks apart into ions. Nobody's staying together in this situation of a strong electrolyte. Question on the differences between those two.
So
Now,
would that mean it's only like partially soluble? Is that the same concept or?
It is sort of the same concept. In this case, these are all going to be really solutions. So they're not going to necessarily dissolve or anything like that, but it's sort of 100% soluble in sort of water, a strong electrolyte. And soluble is not maybe the right word there. Sometimes it is referred to as being dissociated or breaking apart. So it 100% dissociates or ionizes, which are just fancy words of saying it falls apart into ions, basically. And with a weak electrolyte, it's pretty much almost 95, 98% staying together, and just a little bit of it will ionize or break apart, basically. So it's similar to solubility in a sense, but not 100% kind of exactly the same thing. Because usually when we think about solubility, we think about kind of mixing two things together.
Yes.
And in this case, if you had just like a beaker or a test tube of sodium chloride solution, there's nothing really being mixed in there other than it's sort of in a water environment. So it's not exactly the same, but sort of the right idea in that sense. So we usually refer to this more as being something in terms of how much it dissociates or breaks apart or ionizes in water is what we kind of look at it.
Okay, thank you.
You're welcome. Other questions on that? Okay.
Oh, I'm sorry. And will we always be provided those arrows?
Yeah, I probably will in lecture. I think the lab manual and those questions they do provide you, and that's one of the sort of the biggest ways you could kind of recognize the difference. Definitely, if you provided the equation and you see those two arrows, then you definitely know it's weak electrolyte. If you provided the equation, you just see the one-way arrow, I call it, just kind of like heading to the product side. you know it's definitely not going to be a weak electrolyte. So I would say you'd probably be provided for most of that. The only time maybe in the lab you might not be, because they might ask you to write the equation based on what you observed with the light bulb. And again, if you had to do that, it would be the same equation, you know, whatever you're writing. But if you saw the light bulb be very bright, then you know it's a strong electrolyte. So you should use just that one-way arrow. If you saw the light bulb kind of be kind of dim in the video or wherever you watch it, then you know it's a weak electrolyte, and then you should have those 2 arrows in that case. So if you're given the equation, they'll provide the arrow. But if it's something like, you know, based on your observation, you might have to provide your own arrows. And that's sort of what you would want to look for.
That makes sense. Thank you.
You're welcome. Other questions on that? Okay.
I got kind of lost. Like, I don't know. So what are we supposed to do with? We're supposed to. I don't know. I got lost. Like on the homework, like for the electrolytes, like what are we supposed to do? We're supposed to like balance it or something, or
no. So you know, you probably be given an equation, for example. You know, so maybe you're given like this equation, or maybe you're given this equation. And if you're given the equations, what you would want to look at is the arrows. So if you see this one-way arrow, and on the left-hand side you have something that's all together, but on the right-hand side you have the ions, that would tell you it's probably going to be a strong electrolyte. If you look at the equation and you got, you know, something that's all together on the left-hand side, and you have the ions on the right-hand side, but the difference is you have this arrows heading in both directions, that will tell you that it's most likely a weak electrolyte.
So basically all we're gonna, like, we have to kind of be able to recognize the different, like a weak electrolyte, a regular electrolyte, strong electrolyte.
Exactly. And kind of know what it means when I say, you know, if something is a strong electrolyte, what that means is it 100% breaks apart into ions. Nothing stays together. If something's a weak electrolyte, it pretty much all of it stays together, but a little bit breaks apart into ions. So that's sort of the important connection there as well.
Okay, thank you.
You're welcome. Other questions on that? Okay. And there's actually one more electrolyte, which is, I think you mentioned it there. It's a non-electrolyte, and a non-electrolyte. A non-electrolyte will dissolve in water, but no ions will be produced. So a common example would be something like sugar, for example. Sugar is a solid, and if you put it in water on top of the arrow means we're dissolving it in water. You would get sugar that would be kind of aqueous, a sugar solution. Sugar is basically carbons, hydrogens, and oxygen. It's a covalent molecule, same thing on both sides. But there's no ions that are formed because, again, this is covalent or molecular on both sides, so no ions on the product side. And what that means is you get no conducting of electricity. Which means if you take, again, my bad light bulb example, and you put it into a solution that is a non-electrolyte, the light bulb stays off. Doesn't go on, doesn't light up at all. And it doesn't light up at all because of this reason right here. There's absolutely no ions floating around in the solution. Because there's no ions floating around the solution, it's not able to conduct electricity, and we do not get, again, that light bulb to go off. So how could you recognize something that's a non-electrolyte from the other two? The key actually comes here when you look on the left-hand side and you look at the right-hand side. It's the exact same thing. Yeah, it stays together. Everything's the same. There's no ions on the right-hand side, and that's a way you could recognize it. It will also have this kind of one-way arrow, but the difference between that one-way arrow and what we were looking at previously, whoops, where'd it go, was this guy stayed together, ions formed in a strong electrolyte. This guy, same guy on the left, same guy on the right, and absolutely no ions present. So if you're given an equation that looks like that, you can make a pretty safe assumption that that's going to be a non-electrolyte, will not conduct electricity because there's pretty much no ions present. By the way, water, pure water, is a non-electrolyte. It's a bad conductor of electricity. Just so you remember, the water that comes out of your pipes are not pure water. There's actually a lot of ions in it, which is why you would get electrocuted, right? If you were, listening to the radio in the shower or blow drying your hair in the shower, because they put a ton, don't try that at home, by the way. They put a ton of ions in water to kind of clean it. And that's why it conducts electricity really well. But if you took like some deionized water that has no ions in it, it actually is a very bad conductor of electricity. So those are the three types of electrolytes. Strong electrolyte 100% breaks apart into ions. The way you could recognize it in a formula is left-hand side, you have the ionic compound together. Right-hand side, you have the ions from that ionic compound, and it's a one-way arrow. Weak electrolytes stay mainly together. And the way you can recognize those in an equation form is on the left-hand side, you have the compound together. Right-hand side of the arrow, you have the ions, but you have the two arrows in that case, the reversible arrows in a weak electrolyte. In a non-electrolyte, you will typically have same thing on both sides of the arrow, but no ions being formed. And again, that is the way you could recognize that. It will probably have that one-way arrow, but that's the way you can sort of identify the difference between them. Any questions on that? Here's a much prettier picture of light bulbs that I did not try to attempt. Here's our sodium chloride in solution. As you can see, 100% ions, very bright light bulb. This is HF. Mainly, if you look around here, we have the HF together, but a little bit of ions floating around. Light bulb comes on dim. And here's our sugar. Absolutely no positives or negative guys in here. No light bulb comes on. And that's where we're talking about the light bulb. And that's a very common experiment that is done to kind of determine it. So what I was saying earlier was, if you were supposed to write your reaction based on your observations, if you observe this, you should pretty much have something where you got like this, and it should be a one-way arrow, and it should be the ions on the other side. If you have something like this that's dim, that tells you should still have that guy on the left. He will still break apart on the right, but because he's dim, you should put the two arrows. You see this with nothing there in terms of light bulb on, you write basically the same guy that you started with and ended with. And that's how you kind of go from your observations to the formulas. Any questions on that?
Okay, so I have a question. So I'm kind of scanning over the lab manual.
Yeah.
But like another big question it looks like that follows through the lab is like identifying these solutions as polar and non-polar.
Right.
Would a strong electrolyte be polar?
So the polar and non-polar, and again, it's been a while since I actually looked at the lab, but that would probably has to be doing with what we were talking about earlier when we talked about like dissolves like.
Oh, okay.
And it probably would be based off of your observations. So for example, they may mix two things in a test tube. And if it was like a solid that they put in with a liquid and they mixed it and the solid went away and it dissolved, then, if this was water, then this is probably ionic in water. And that's how you would know. Ionic for the solid, polar for the water, like we talked about, ionic and polar being soluble. Or if you mix two liquids and one was, say, water and one was some other liquid, for example, and they also mix together. We know since one is water, then the other one is probably a polar liquid as well, because water is polar. So remember, that's that like dissolves like, and that's probably based off of some observations, I would assume.
Okay. Oh, I understand. Okay. Thank you.
You're welcome. Okay, one last topic here I think I'm gonna wrap up with. So we're not here for 5 hours, but we'll look at one more topic. And again, this should hopefully get you through most of it. And probably on Monday, we'll try to get through the other part before you go to the lab. But I do want to talk about equivalence and sort of what they are. a lot of times body fluids are given in terms of equivalents, and equivalents, you know, they're basically, you could think of them almost like a conversion factor, if you will. That's sort of how we use them in this class. And it's really all based on the charge. And it's actually not based on, is it a positive charge or a negative charge? It's actually based on the number that goes with the charge. So whatever the number that goes with the charge. And what that means is we could write conversion factors to use in calculations. So for example, if I had a calcium ion, I could say that 1 mole of calcium gives me 2 equivalents. Where does the 2 come from? It comes from the actual number from the charge. And that's where the 2 comes from. And we could use this as a conversion factor. We could say in a 1 mole of calcium, there are 2 equivalents. Or we could use it like a regular conversion factor. 2 equivalents is 1 mole of calcium. And it doesn't matter if it's positive. It doesn't matter if it's negative. This is phosphate. And I could say in 1 mole of phosphate, there would be 3 equivalents. The 3 coming from the actual number on the charge. We could also do 2 conversion factors for those guys. And, you know, if you had something like sodium, for example, we could say 1 mole of sodium ions gives us 1 equivalent. And again, it's 1 is the charge here, and that's where the equivalents come. Obviously, we could write the same sort of conversion factor as well for that guy. Now, sometimes equivalence and concentration is given in terms of equivalents, like in IV bags and sometimes like that. And it's usually given in kind of 2 units, either equivalents per liter or sometimes what is referred to as milliequivalents per liter. So what is the difference between these two? One's equivalents, one's milliequivalents. It's the same conversion as 1,000 milliliters is a liter. There would be 1,000 milliequivalents in a equivalent. So it's kind of the same sort of conversion as we do with like milliliters and liters. So sometimes we're asked to figure out what is the concentration of a solution based on, you know, what it would be in equivalents per liter or milliequivalents per liter. So let's take a look at one here. Let's say we had a 0.025 moles per liter solution of Na2SO4. And what we want to know is what is the equivalence per liter of the sodium ion and the sulfate ion. And we'll do both. What is the milliequivalence per liter of the sodium ion and the sulfate ion? So when we look at something like sodium sulfate, it is going to break apart into 2 sodium ions and 1 sulfate ion, right? And that's basically what the formula means, right? That's what the 2 means, right? There's 2 of these sodium ions, and there's basically 1 of these sulfate ions that are present. Now, if this entire thing had a sort of a concentration of 0.025 moles per liter, we could actually do a mole to mole relationship here. And what we see is for every 1 mole of the sodium sulfate, we get 2 moles of sodium ions. It's kind of like how it breaks apart, essentially. It's a 1 to 2 relationship, which means if we do that little conversion, this gives us 1 mole of the whole thing, gives us 2 moles of just the sodium ion. The moles of the whole thing will cancel, and we essentially will end up with 0.050 moles per liter of sodium ions that are present. So really, we're just trying to find the concentration of just the ion by itself. And we could kind of do what is sometimes referred to as a mole to mole relationship, or you could just think of it as when this sodium sulfate goes for a swim, you get basically 2 sodiums for every 1 sulfate that's made. So it is twice as concentrated in terms of the sodium ion than it is the whole thing. And that's really what we did here, right? We basically multiplied it by 2 and we get a concentration that's twice as concentrated. It is a 1-to-1 relationship in terms of when that guy goes for a swim as to how much sulfate that we get, which means we could do the same calculation. And the difference is it's a 1-to-1 relationship, which means it is going to come out the exact same number in this case, because it's basically multiplying by 1 and dividing by 1. And these guys again would cancel, and we would get 0.025 moles of sulfate per liter of solution, basically. So if we had really a solution, and we could really kind of pick it up from this point here, if we had a solution of sodium sulfate, and like I said, when that thing kind of goes in for a swim, we're going to get twice as much, as you can see by the number, right? 0.05 is twice as much sodium ions floating around than there are sulfate ions floating around. So we can use our equivalents to help us do the conversion. So let's talk about our equivalents in this case. We have a sodium ion, which means, as we talked about on the previous page, 1 mole of sodium would have 1 equivalent. And again, the 1 comes from the charge. Also for our sulfate in this case, 1 mole of sulfate gives us, hopefully you get the idea here, it should be 2 equivalents in this point. Again, the 2 is where we get that from the charge. And we're going to use these really as conversions, and we're going to convert each of these separately into their equivalents per liter and milliequivalents per liter. So I'm going to flip the page because I need somewhere to write. So everybody good? Yes. All right. So let me take the first one. We'll start with sodium. So basically in that solution, or if you're just given the fact that you have 0.05 moles per liter of sodium ions, we want to get to, if you remember, equivalents per liter and also milliequivalents per liter. So what does that mean? Well, if we look at the bottom part, that is liters, and the bottom part on both of these are liters, which means we don't have to do anything to the bottom part. The bottom part's fine. The top part is what we need to change. We need to change the moles to equivalents. So as we saw on the previous page, we could use this conversion to do that. So what we're doing really is a conversion factor to go from moles to equivalents. So if we do that, based on that, that 1 mole of sodium ions gives me 1 equivalent. And again, that is that relationship that we had on the previous page. And essentially what we're going to be doing is using as a conversion factor, the moles of sodium cancel. And I could do this math, I think. We end up with 0.05 equivalents per liter. Again, nothing changed on the bottom, of sodium ions. Any questions on that there? Now, that would be one answer, right? That would technically be the concentration of sodium ions in my solution based on equivalents per liter. The other thing that we want to solve for is milliequivalents per liter. So really the last thing that we need to do is the conversion between equivalents on top to milliequivalents. And again, we would use, where'd that guy go? This relationship here, that there are 1,000 milliequivalents and 1 equivalence. So if we do that calculation, and 1 equivalent, there is 1,000 milliequivalents. The equivalence would cancel. I won't cross it because this is an answer, but we will be left with milliequivalents. So we're basically just going to multiply it by 1,000 in this case. And we will end up with 50 milliequivalents per liter of sodium ions that are floating around in that solution. And these are what are sometimes referred to as the concentration in milliequivalents per mole per liter and equivalents per liter. And by the way, this original number, the moles per liter, was also a concentration. This is actually what is known as the molarity of the solution, which is moles per liter. So those are all 3 different ways that we could express the concentration of the sodium ions that are floating around in the solution is 0.05 moles per liter, which is the molarity, 0.05 equivalents per liter, which is concentration and equivalence, and 50 milliequivalents per liter, which is this concentration in obviously milliequivalents. Now that's, if you think about the solution, only one part of the solution, right? That is just the concentration of those sodium ions floating around in that solution. We still have the sulfate ions, right, floating around in that solution. So we could do the same calculation for the sulfate. So we're going to start with the original concentration of the sulfate, which was that number there. So our original sulfate concentration was 0.0250 moles per liter of sulfate ions floating around. And again, by the way, that is the molarity, which is moles per liter. And that's a unit of concentration. We're going to do the same conversion, but it is different because this is sulfate. We saw we had a different relationship in terms of equivalence. Because the sulfate has a 2 for its charge, it gives off 2 equivalents in this case. So we're going to use that as our conversion factor, where we would have 2 equivalents on top, 1 mole of sulfate on the bottom, and the moles will cancel out, and that will give you 0.05 equivalents per liter of sulfate. We can then do the same conversion we did on the top one and convert it into milliequivalents by using the same conversion. Again, the equivalents would cancel, and that would leave us with 50 milliequivalents per liter of the sulfate ions that are floating around in that solution. This again would be the concentration in milliequivalents per liter of sulfate in that solution floating around. This would be the concentration of sulfate in equivalents per liter. And this original guy would actually be the concentration of sulfate in molarity, which is moles per liter. First off, question on that calculation there. You might also notice something kind of interesting and a very good way to check yourself to make sure you didn't screw up. This is a sodium sulfate solution. The concentration of the sodium ions in equivalents per liter is exactly the same as the concentration of sulfate ions in equivalents per liter. And if you go over to milliequivalents per liter for both of them, they are exactly the same. And the reason why they're exactly the same is, if you remember from when we did nomenclature, when we put something together like this, which is +1 and -2, the goal is to balance out the charge, right? In the simplest way possible, which means the overall charge of positive guys floating around in that solution and the overall charge of negative guys floating around that solution should always be the same. Because when you have a actual solution of an ionic compound, all the positive charge needs to balance out all the negative charge. And what that translates is, if you calculated the equivalence per liter for an ionic compound, the positive ion in that solution's overall concentration should match the negative ion's overall concentration. And that's kind of the purpose of when we put them together, we try to balance out the charge. Any questions on that there? All right, I'm gonna lay it up there. That hopefully should help you. And let me just show this actually one thing here. I think, where'd it go? There it is. Here's sort of a table. I think you have some more in your book. And again, you could see in terms of equivalence, just to wrap up on this, we have our sodium with a +1, has 1 equivalence. Calcium +2, 2 equivalents. Iron +3, 3 equivalents. So again, it doesn't matter if it's negative charge or positive charge. We basically will use these in this sort of fashion as a conversion factor to really convert units of concentration. And again, the 3 is where the 3 comes from. So this should cover a lot of what's in that sort of experiment. It's also chapter 9, obviously, officially. And I hope this helped. I thank you for hanging out.